In last class, we had started discussing the concept of what is a transform and why transform domain signal processing is useful. Today, we will formally define these notions and hopefully get to the point where we start discussing the discrete Fourier transform. So as I talked about earlier, in this transform domain signal processing discussion, I will switch between the sequence notation, which is xn not equal to 0 for n 0, 1 up to n minus 1. We will always be working with finite duration sequences, and I will often write that as a vector in an n-dimensional space where the first element is x0 and the last element is xn minus 1. Okay, so what is a transform? If you think of this sequence as a vector in Rn, then a transform is effectively nothing but a change of basis of this sequence. Okay. So the idea is that your x, which is in Rn, it's given by the canonical bases, which are the canonical bases in Rn are simply the identity matrix, right? The identity matrix, which has 1, 0 all the way, then 0, 1, and 0, and so forth, 1, right? This defines, this is called the canonical basis in Rn. And whenever we are talking about a sequence in time domain, in spatial domain, we are talking about effectively a vector in n-dimensional Euclidean space with these canonical coordinates. And a transform effectively does a change of basis, and so you get a new vector theta, which is given by t times x. So x is your vector, and this t is a matrix of dimensions m by n, with m bigger than or equal to n, and rank of t equals to m. So rank means simply how many linearly independent rows or columns of this matrix you have. Rank of t equals to n. So it has n linearly independent columns, it has m rows, and m can be greater than or equal to n, and rank of t equals to n means that we can go back to x. That's sort of the basic requirement. And this theta, so in the world of transform domain signal processing, this theta, which is now an m-dimensional vector, okay? You multiply an m by n matrix with an n by 1 vector, you get an m-dimensional vector. This vector is called transform domain coefficients. Okay. Now, what does transform domain processing means? The transform domain processing means that you are given a signal, you take that and convert that into its transform domain coefficients. Then you do processing on those coefficients, which is often nonlinear. Okay? And since it's nonlinear, you cannot implement that using a filtering operation. You do some sort of processing in the transform domain, and then you may or may not go back to the original domain. So the typical transform domain processing has the following blocks. So you start with X and you multiply that with the matrix T to get the transform domain coefficients theta. And then you do some sort of processing, which the processing depends upon the end goal that you are after. You might be interested in reducing noise in your image. You might be interested in compressing your image. You might be interested in some other aspect. And the processing will be a function of that. So you take these transform domain coefficients, you do some manipulation of those coefficients to get back another vector theta hat, which is still m-dimensional, but the coefficients in there are different from the ones you started with. Now, in many cases, you stop actually at that level if you are only interested in doing some sort of analysis. For example, if you are given a signal and you are only interested in finding out what kind of frequencies are present in that signal, then you may go into a transform domain, let's say a discrete Fourier transform domain, and you do some plot and you look at which frequencies are present and then you stop there. Okay? Your only goal was to figure out which frequencies are present. But in some other cases, you actually want to go back to the original domain that you are working with. The example of that will be you have an image, you compute its, let's say, wavelet transform coefficients. Your goal is you want to reduce the storage size of that image without affecting the visualization of the image too much. So you will do some manipulation of the wavelet coefficients, but after you have done the manipulation, you want to go back to the image that you can visualize. Okay? So after the processing, you may or may not want to go back to X hat in the original domain. And how you go back to the original domain is by taking what's known as the pseudo-inverse of your matrix. Okay? Remember, we are working with a matrix which is m by n. It is not a square matrix. We are saying m can be greater than n. Now, if you have taken linear algebra in your undergraduate, then you would know that inverse only exists if you have a square matrix. So to go back, to take the inverse, to go back to the original domain, you actually need the pseudo-inverse, which I won't go into the formal definition, but based upon the way we have defined that the rank of our matrix is n, which means that all the columns of my matrix are linearly independent. Okay? Under that condition, the pseudo-inverse of a matrix is defined as simply T Hermitian T inverse, the whole inverse, T Hermitian. Okay, where Hermitian, for those who don't know, if I take the Hermitian of a matrix is equivalent to taking the transpose and the conjugate of that transpose, or the other way, it doesn't matter. You can first take the conjugate and then take the transpose. Okay, so the Hermitian simply means you take your matrix, you take its transpose, and then you take the conjugate of its entries. So if you look at this, of course, this T Hermitian T, this is n by m matrix getting multiplied with m by n matrix. So this is an n by n matrix. This is a square matrix. You can take its inverse because it has linearly independent columns. The original matrix had linearly independent columns. So T Hermitian, T inverse, T Hermitian. Okay, so how you go back to x hat is defined as T Hermitian T inverse T Hermitian theta hat. So that's the usual steps in the transform domain signal processing. You first multiply by a matrix, go to the transform domain, do some sort of processing, get theta hat, and then you may want to go back to the original domain by doing multiplication with another matrix which is given by T Hermitian T inverse T Hermitian. Okay. Now, why is this a transform? The definition, if you want to think about your earlier transform definitions, if I don't have this processing step, what we want is that x hat, so if theta hat was equal to theta, what we want is that x hat should be equal to x. So I go into the transform domain, and if I don't do anything else, I just want to go back to my original domain, I should get back the sequence I started with. Okay? So in that case, if we say that assume theta hat equals theta, which is of course defined by Tx, then we want that x hat should be equal to x if T is a transform. And that is trivial to see in the case we have defined. So if I say x hat, I have defined that to be T pseudo inverse T pseudo inverse theta, which is equal to T Hermitian T inverse T Hermitian T x. Okay, so I have just input the value of theta in here, and I have input the value of the pseudo inverse. Now, as long as we don't change the order of multiplication, whether I multiply matrix multiplication is associative. So if I am multiplying matrices, I can multiply them in any order I want, as long as they don't change the order of multiplication. So I can simply write that as T Hermitian T inverse T Hermitian T times x. Okay. And so this is a matrix T Hermitian T. This is and we are multiplying a matrix. So if let's say I define this as A, I'm multiplying A with A inverse. So what is A inverse times A? That is just identity, and I get back x. Okay. So indeed, if I don't do any processing of my transform coefficients, I just get back the original coefficients that I started with. So based upon that, we can define the usual way of transform domain coefficients. We can call theta the transform domain coefficients, or this equation theta equals to Tx as the analysis equation. So you can call theta as analysis coefficients or transform coefficients. It's the same. And taking x and multiplying that pseudo inverse times theta, which means you are taking your analysis coefficients and you are resynthesizing your original signals. So that will be called the synthesis equation. Okay. Now, we won't go into too much detail, but a good transform is also one which has a small condition number. A condition number means you are trying to basically take the inverse of T Hermitian T if t does not have a good condition number, then when you try to take that inverse inside a computer, this thing can have huge numerical errors. Okay, so we won't spend too much time or say much further than that. You can go on to Wikipedia and look up what condition number technically means, but we want our transform to ideally have a small condition number, which means that calculations involving this transform inside a computer are stable. Okay. You don't have huge numerical errors. Okay, so that's the general definition of transform, which I presume you might not have seen before, because typically we work with orthogonal or orthonormal transforms. So let's look at special cases of these transforms. The most well-known transforms are those that are orthogonal transforms, and those are the transforms that we will work with. So an orthogonal transform is the following. We'll define it. First of all, an orthogonal transform means that our T is going to be a square matrix. Okay. You start with an n-dimensional signal, and when you transform it to a different basis, you still have an n-dimensional transform domain signal. Okay. And the other condition we are going to impose here is that if I denote the columns of my T, so if I write T as T1, T2, up to Tn, okay, where Tn, Ti, which is a column vector, is an n by 1 vector. So the other condition we are going to impose for our orthogonal transform is that Ti, Tj, inner product of Ti and Tj, which in the case of vectors is defined as Tj Hermitian Ti, okay, that is equal to 0 for all I not equal to j. So if you take the inner product of two columns of your matrix, then the inner product is 0 if the columns are not the same. Okay. In that case, it turns out that T Hermitian T, okay, it's easy to see in that case, that is simply T1, T2, Tn Hermitian T1, T2, Tn. Okay. So this is an n by n matrix, this is an n by n matrix. Right. You get T Hermitian T is a matrix where each entry of that matrix is inner product of any two columns. So the first entry is going to be inner product of T1 with itself. Okay. The second entry is going to be the inner product of T1 and T2, and so forth. Okay, so on the diagonal, you are going to have inner products of vectors with themselves, in the off diagonals, you are going to have inner products of different columns. Now we just said that an orthogonal transform, if you take inner product of two different columns, the answer is 0. This means that everything in this matrix on the off diagonals here and here, that will be equal to 0. Okay? So all you will be left with is a diagonal matrix. So you will simply have a diagonal matrix which will have on the diagonal T1 Hermitian T1, T2 Hermitian T2, Tn Hermitian Tn, and 0 everywhere else. Okay. Let's make another simplification and let's assume that Ti Hermitian Ti. So if I take the inner product of my columns with myself, which is simply equal to taking the sum of the squares of all the entries in my columns, that is equal to some number alpha for all I. Okay? In that case, I get T Hermitian T is simply equal to alpha, 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 and 0 everywhere, which is simply equal to alpha times an identity matrix. Okay? So an orthogonal transform, this implies that an orthogonal transform with all columns having Ti Hermitian Ti equal to alpha has T Hermitian T equals to alpha times identity. Now what was the definition of pseudo-inverse that we need for our synthesis operation? So pseudo-inverse was defined as T Hermitian T inverse T Hermitian. Okay. So this means that T Hermitian T, if I want to plug it in here, T Hermitian T inverse, what will be that? That will be inverse of alpha, because that is a scalar, times the inverse of identity, which is just identity. So that will be alpha inverse times identity. This means the pseudo-inverse will be simply equal to, if I plug in this value here, that will be equal to alpha inverse T Hermitian. So if I now talk about for orthogonal transforms with inner product of columns equal, then the analysis equation of course stays the same. There is no advantage of using orthogonal transform in the analysis equation. I have theta, which is equal to T times X. Okay. But let's look at the synthesis equation in that case. The synthesis equation in that case simplifies a lot. We have X equal to T pseudo-inverse theta, but that is simply equal to alpha inverse T Hermitian theta. So when we did not have an orthogonal transform, we were inverting a matrix. Now remember, all of these operations we are trying to do inside some sort of a digital system. When we did not have an orthogonal transform, we were asking our digital system to invert a matrix here. Okay? we had T Hermitian T inverse. We were inverting an n by n matrix. I'm sure in your undergraduate, all of you have inverted by hand 2 by 2 and 3 by 3 matrices. Well, inverting n by n matrices in digital systems is not a cheap thing to do. It costs a lot of time. But in the case of an orthogonal transform, all you are doing is inverting a scalar, which is just dividing by a scalar. So that is one key advantage of using orthogonal transforms. The synthesis equation of orthogonal transforms is much, much simpler than non-orthogonal transforms. Okay? And in this class, we will only work with orthogonal transforms, even though non-orthogonal transforms are used in real world for various other reasons. But computational simplicity and analysis simplicity are two of the key reasons we want to stick with orthogonal transforms. In addition to orthogonal transform, there is a special type of an orthogonal transform which is called orthonormal transform. Which, as the name implies, is an orthogonal transform if T is orthogonal with equal norm columns, i.e., so this is the definition of the 2 norm, which is simply defined as Ti Hermitian Ti. So in that case, equal norm columns and alpha equals 1. Okay. In other words, if Ti Hermitian Ti equal to 1 for all I and T is an orthogonal transform, then this means that T is an orthonormal transform. So normal means simply that the columns are normalized. Okay, the columns are normalized to have unit magnitude squared. The sum of squares of their entries comes out to be 1. And whether you have orthonormal transform or orthogonal transform, the only difference is between alpha. So in that case, your analysis equation again doesn't change. That stays theta equal to Tx, whatever your T is, but your synthesis equation simplifies further. That becomes only x equal to T Hermitian theta. Okay? So regardless of which transform you are talking about, you are always doing the same analysis. You multiply your vector of representing your sequence with a matrix, you get your coefficients. But how you go back to your original sequence depends upon whether you have an arbitrary transform or an orthogonal transform or an orthonormal transform. Okay. Okay. So as I said, orthogonal, orthonormal, it doesn't matter. In both those cases, it's the same. There's no basic difference between the two transforms, whether you have normalized columns or not. But whether you have an orthogonal transform or not, that makes a huge difference. And in this class, we are only going to talk about orthogonal transforms and examples of transforms that are orthogonal, although you can have non-orthogonal transforms too within the same category. So you have the discrete Fourier transform, which I'm sure you have studied in your undergraduate and will study it again here. that is used both for processing and analysis. Discrete Fourier transform serves both the processing purpose and the analysis purpose in many applications. You have discrete cosine transform, or DCT, which is very similar to the DFT, but it's a real value transform. You have what's known as the Hadamard transform, which is a matrix which is given by just, it has binary values. It takes either value +1 or -1, okay, with a very particular structure. You have wavelet transform, and the reality is we should be calling it as wavelet family transform, because wavelet transform is again a general notion of a transform. It depends upon what final wavelet, mother wavelet that you decide to use, which we'll cover later. Okay, and even within wavelet transforms, actually you can have non-orthogonal wavelet transforms, but we won't go there. You have short time Fourier transform, which again is used for both analysis and processing, although it is sometimes used more often for analysis than processing. And many more. Now, all of these transforms basically have applications depending upon what you want to do. There is no one single transform that you can say, let's use this transform, and if I learn this transform, I can solve every problem in the world. There are different transforms because some transforms have some advantages and some transforms have other advantages, depending upon the application that you are going to work on. And it's really the person who is implementing the application can tell which transform I should be using, or playing with different transforms and coming to a realization that let me use the following transform. And as I said, in recent years, with the computations becoming cheap, it used to be a big issue because we had systems which couldn't perform that many computations. In recent years, with the computations becoming cheap, actually non-orthogonal transforms are gaining more and more traction, studied under, for example, frame theory. So we won't even go near the non-orthogonal transforms, but just trying to point out to you that it's not as if the world of transform ends at orthogonal transforms. Okay. So our goal is, I gave you a general definition of transform because I don't want to repeat what will be the analysis equation or what will be the synthesis equation for different transforms, as long as you get the basic concept. We are again taking the approach that we are studying the definition of a transform from an abstract perspective. Now we'll try to go into specific, and we'll see what does, for example, T look like in one case versus the other. Okay. So the first thing we are going to cover is discrete Fourier transform, or DFT as it is commonly called. And DFT is used for many purposes. We'll talk about the applications later. We'll also go back to the definition of DFT that you have seen in your undergraduate, but we'll first start with the definition that we are posing as the definition of the transform. So if we want to define a transform, what we really need to define is the matrix that defines that transform. Okay. So, and in the case of DFT, I'll be using, instead of T, because it's just a dummy matrix, I'll be using the matrix U. Now DFT is an orthogonal transform, and so this U will be an n by n matrix. To avoid writing this exponential again and again. I'm sure you have seen this, e to the minus j 2 pi over n. That in shorthand is represented as capital W sub capital N. Okay. So how is the DFT matrix defined? The DFT matrix is defined as, let's go column by column. We need to define n columns. The first column is Wn0. The first entry is 0th power of that. Okay, so Wn0 and 0th power is equal to Wn00. Then the same one, Wn0 and the first power of that. And we keep on going down, Wn0 n minus 1. Now you can of course simplify it because all of these have power 0, which means they are all 1. Okay, the first column is all 1. But right now I'll just keep it that. Now the second column is Wn1, its 0th power. Wn1, its first power, and keep on going Wn1, its n minus first power. And that's the way every column is defined, such that the last column is Wn n minus 1 and its 0th power. Okay, Wn n minus 1 and its first power. And that keeps on going up to Wn n minus 1 and its n minus 1 power. Okay. Now, this is one definition of this DFT matrix, which is non-normalized. As we will see, then the columns, if we look at the energy in the columns, that is not 1. So it's really, the way I have defined it, DFT is an orthogonal transform, not an orthonormal transform, the way I have currently defined it. Some people do define DFT as an orthonormal transform, and we'll see what that simply means. That's just a scaling factor. Okay. I just want to point out that this DFT matrix is actually an example of a Vandermonde matrix. Vandermonde matrix, which is defined as follows. A Vandermonde matrix in general is given by, you are given n numbers, alpha 1 up to alpha n, and every column is defined by powers of those numbers. So alpha 1 1, alpha 1 0 up to alpha 1 n minus 1, alpha 2 0, alpha 2 1 up to alpha 2 n minus 1, alpha n 0 up to alpha n minus 1. Effectively, each column is just a geometric progression. Each column is a geometric progression of a number. So to say that the DFT is a transform, we of course have to argue that the rank of the DFT matrix is n, but that follows from some of the properties of the Vandermonde matrix. So DFT matrix is a Vandermonde matrix with simply alpha 1 equal to Wn0, alpha 2 equal to Wn1, and alpha n equal to Wn n minus 1. Okay, you can compare the two definitions, and it turns out it's exactly a Vandermonde matrix with a specific alpha 1, alpha 2, and alpha n. And there is a property of the Vandermonde matrix which says that if alpha 1 up to alpha n are distinct, then a rank of V equals to n. Okay. And since Wn0, Wn1, Wn minus 1 are distinct, therefore rank of U equal to n, and this means that DFT is indeed a transform. Well, in fact, you could check it other ways too. In fact, it is an orthogonal transform because any two columns of this matrix are orthogonal to each other. So in fact, DFT is an orthogonal transform. Which means that if I write my, so if I write my U equal to, I write different columns, U1, U2, up to UN, then UI and UJ, inner product of that is 0 for all I not equal to J. And proving that is very easy. So let's look at what is the definition of UI. Remember, it's a vendor. If you want to remember what do the columns of the DFT matrix look like, they are just geometric progression of Wn to Wn times over some integer, all the powers of that. So the ith column is simply Wn(i) minus 1. Okay? So the ith column is simply Wn(i) minus 1. Its 0th power, Wn(i) minus 1. Its first power up to Wn(i) minus 1. Its n minus first power. Okay? Is the ith column. So if I want to write down UI and UJ, which is simply equal to UJ Hermitian UI. Okay. So Hermitian is that I just multiply the corresponding entries but take the conjugate of the other entry. So what does UJ Hermitian look like? That is, I of course take the transpose. So I have W and I take the conjugate. So I have Wn minus J minus 1, 0 up to Wn minus J minus 1, N minus 1 and times UI. So a row vector is being multiplied by a column vector. I just add their respective entries now. So n equal to 0 to n minus 1. I can write that Wn I minus 1n times Wn minus J minus 1n. Okay. Now since these are simply exponentials, I just add up their exponents. So I get Wn I minus 1 minus J plus 1 n equals n equal to 0 to n minus 1 Wn I minus J times n. Now whenever we see a summation with changing exponentials, so we have a geometric sum, we just want to use the geometric sum formula, right? That is 1 minus ratio to the nth power divided by 1 minus r. Now remember, we are still talking about I not equal to j, okay, which means that this ratio, so this is not 1. So if I apply the geometric sum formula, I get Wn I minus j, and there are n entries, so times n over 1 minus Wn I minus j. Now Wn I minus j, this numerator is equal to 0 because Wn I minus j times n, which is simply equal to e to the minus j 2 pi I minus j. Okay, so we have e to the minus j 2 pi times an integer, because I is an integer, j is an integer. This has to be 1. So this is equal to 1, and 1 minus 1 is 0. So indeed, the inner product between any two columns of my DFT is 0. So DFT is an orthogonal transform. Okay. So for orthogonal transform, we know DFT is an orthogonal transform, and this means that if I talk about U Hermitian U, that will be simply a diagonal matrix where the first diagonal will be U1 Hermitian U1, the second diagonal will be U2 Hermitian U2, and the last diagonal will be UN Hermitian UN, and everything will be equal to 0. So let's find out what do the entries in this look like. Okay. Well, in that case, we just come back to this equation, and instead of I minus j, right? Instead of I minus j, now we want to compute the inner product of two columns when both the indices are same. Okay, so I can do the same exact thing, and I will end up with, so I'm now going to take a little shortcut and say that in that case, UI Hermitian UI is simply equal to, so this will be Wn0n, so that will be simply n equal to 0 to n minus 1 Wn0n, which is simply equal to capital N. Wn0n is 1, so you are taking summation sum of n ones, that's n. And it doesn't matter what I is. So in fact, U Hermitian U is simply equal to n, 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 or that is equal to n times identity. So we call this number alpha. So alpha in the case of the DFT matrix is alpha equals n. Okay. Now, if I want to talk about analysis equation, in the case of DFT, that is the same. And in the case of DFT, since we are going to go to the book notation, I'm going to use the transform domain coefficients. Instead of calling them theta, I'm going to write them as capital X, okay, which is also in Rn. That is equal to u times little x, okay. So regardless of the transform, this analysis equation is not going to change, but the synthesis equation that is little x equals u Hermitian capital X times alpha inverse. Right? If you go back and look at your notes, we defined when alpha is not equal to 1, our inverse transform or synthesis equation comes out to be alpha inverse times u Hermitian, which means it will be equal to u Hermitian over n times capital X. Okay. Now there is another fact. If you look at so let's go back to the expression. If you look at this u and you do u transpose, look at the first row and the first column. They are exactly the same. Okay? And similarly, the second row and the second column. The DFT matrix is in fact a symmetric matrix, which means that u transpose equals u, which means that u Hermitian, which is defined as ut conjugate, that is equal to u conjugate. Okay? So if you want to define and u conjugate simply means that you will put minus signs at every entry of this expression. Okay? So even u Hermitian is going to be a van der Waals matrix, but the first entry will become, instead of wn0, it will become wn minus 0. Okay? So u Hermitian equals u conjugate, which is simply equal to wn00 minus wn minus 0 1 up to wn minus 0 n minus 1, wn minus 1 0, wn minus 1 1 up to wn minus 1 n minus 1, and so forth up to wn minus n minus 1 0 and wn minus n minus 1 n minus 1. Now, some people work with a DFT matrix which is orthonormal rather than orthogonal. So how do you make a transform from orthogonal to orthonormal? If you are given one other way of writing an orthonormal transform is that u Hermitian u, if u Hermitian u, and let's use tilde because we are talking about a different transform, equals to identity, then this implies that u tilde is an orthonormal transform. Okay. In the case of an orthogonal transform with equal magnitude columns, we get u tilde Hermitian u tilde as alpha times identity. Okay, so one of the ways we can make, so if U Hermitian U is alpha identity, we can get an orthonormal transform by defining another transform U tilde as U over square root of alpha. If you do that, then what happens? U tilde Hermitian U, that is equal to U tilde, that is equal to U Hermitian U over square root alpha times square root alpha. But U Hermitian U is alpha, and square root alpha times square root alpha is alpha, so you get identity. Okay? So there is actually an orthonormal variant of DFT. There's actually an orthonormal variant of DFT that sometimes are defined in the textbooks, which is defined by, so alpha in the case of DFT is, alpha is n. So some people will define DFT transform as U 1 over square root of n times U. Okay? Remember, in the case of an orthonormal transform, the analysis and synthesis of equations are simply multiplying by U and U Hermitian. Okay? So in that case, your transform becomes 1 over square root of n and Wn00 up to Wn0n minus 1, Wn n minus 1, 0, Wn n minus 1, n minus 1. In the literature, sometimes this is called normalized DFT matrix. I believe this version, without the normalization, you can go into MATLAB and generate this matrix by giving the command dft-mtx. It will generate a matrix which will be this DFT matrix. Okay. So we will stick with the non-normalized DFT because your book is defining your DFT in a non-normalized fashion. So for the non-normalized DFT, we are going to use this matrix, which is U. And our analysis equation is going to be capital X equal to U little x. Now, if you start writing down the entries of this, you actually get back the non-matrix vector type expression that you have seen in your undergraduate. So if I define my capital X as capital X0, capital X1, up to capital Xn minus 1, and I already said my little x is little x0 and little x up to little xn minus 1. And just try to write down the first entry of this. So the first entry of this x is the first row of my DFT matrix multiplied with this little x. So if I write down my x of 0 is simply summation of xn, n equal to 0 to n minus 1, e to the minus j 2 pi over n times n0. Right? And similarly, I can write it for every value. In particular, my xk for k between 0 and n minus 1 is defined to be n equal to 0 to n minus 1 x of n e to the minus j 2 pi over n nk. Okay. And this is in general what you might have seen being called the discrete Fourier transform. But that exactly comes from, if I'm just multiplying the rows of my matrix with my signal, and I keep on getting these values. So you can define your discrete Fourier transform either by recognizing this formula or just understanding that it's just a multiplication of this matrix with my signal. Okay. Similarly, in the case of the non-orthogonal transform, the analysis equation is little x equals 1 over n. Okay, because our alpha we are doing non-orthonormal. So our alpha is n. So alpha inverse is 1 over n times u conjugate. U Hermitian is u conjugate. We already saw that. Times capital X. Okay. So the synthesis equation, which is we are trying to get back our signal from the Fourier coefficients. So these x tildes are sometimes also called DFT coefficients. So if I think of that way, then I have x0 up to xn minus 1. That is equal to 1 over n wn minus 0, 0 up to wn minus 0 n minus 1 and wn minus n minus 1 0 up to wn minus n minus 1 n minus 1 times x0 up to xn minus 1. So this means if I just look at the first entry, that is x0 equal to 1 over n because of the outside 1 over n, summation k equal to 0 to n minus 1 x of k e to the minus j 2 pi over n times k0. Okay. Or in general, my x of k for k between 0 and n minus 1 is simply given by 1 over n summation k equal to 0 to n minus 1 x of k, which is the Fourier coefficients, e to the minus j, sorry, this should be e to the plus 2 pi over n times kn. Okay, which is what you might have read as the inverse DFT expression or the inverse DFT formula. Okay. Now, if you understand that this difference between orthogonal and orthonormal transform, in the orthonormal transform, some books then define, since we talked about how do you make orthogonal transform into orthonormal transform by dividing your original matrix by 1 over square root of alpha. So that will be 1 over square root of n, and you would get 1 over square root of n here and 1 over square root of n here, and some books indeed define DFT in that way. Okay, the only difference between those two is one makes it orthonormal and the other keeps it orthogonal. So we'll end at here, and next time we'll pick up from what does DFT in general mean in relation to the discrete time Fourier transform and other such details.